Hi everyone, my name is Suraj, and today we're going to be walking through the midterm 1 from the spring 2019 iteration of Data 100. Let's get into it. So I know normally we write directly on the worksheet, and we'll do that for all of the other questions, but question 1 on this midterm has us write several queries both in Python and SQL. So I thought, why not actually write the code in a notebook and experiment with different things. Hopefully that'll make writing this code slightly easier, or understanding the code slightly easier. But for the remaining questions, we will do the typical iPad thing. Okay, so let's run these cells, blah, blah, blah. So we're told in this question that we have 3 tables. One is called cities, which contains the name of a city and its population in thousands. One is called names, and it has the abbreviation of a state's name along with the state's full name. And then one is called states, which contains the abbreviation of the state name and the number of people that live in that state in millions, I believe. Yeah, in millions. Okay, and so we're given 3 queries, each of which we want to write both some pandas code to evaluate it and some SQL code to evaluate it. Okay, if you're watching this in fall 2019, SQL is not in scope for midterm 1, but it may be in scope for the final or midterm 2 or something. And if you're watching this in a semester after fall 2019, then who knows what's in scope. But that's just a quick note. So for part A, what we want to do is create a table that is the same as cities, but with an additional column AB containing the abbreviation of the state in which the city is located. So for example, we basically just want to recreate this table with an additional column that looks something like CA, NV, and NJ. So a natural way to want to do this would be to somehow merge the cities and names data frames on these values, California, Nevada, and New Jersey. But if you look at the template that's sort of given to us, there isn't really any place for us to do a merge. Okay, and so the general idea of what we will do is this. We see that we're changing the index of the names data frame, or this temporary copy of the names data frame. What we're going to do is change the index to be whatever is in the full column. And so that when I index into this new version of names, my row indexer will just be the full name that I want to get the abbreviation of. And then there will only be one column at that point, which will be abbreviation. And so then when I do this, it'll give me just a list of abbreviated names, since the column I'm going to be calling is abbreviation, and the indices will be the full names. But that's one step in the future. What we want to do first is figure out how to extract just the names of the states from the city column in cities. So to do that, we'll look at cities, city column, and then do .str.extract. What we need to do in here now is provide some regular expression that will match just the California, Nevada, and New Jersey parts. Okay? And so what we're actually going to do is use the grouping functionality. And so what we need to do is first specify, okay, the end of my string should look like comma, space, and then the name of a state. Okay, and we can assume that there's exactly 1 comma in each city value. Okay, but what we want to extract is everything after the comma and space. Okay, so I put comma, space, and then somehow I need to extract the name of a state. Okay, and so theoretically, what I could do is put \W, which will match any letter, and a plus. Okay, and so what this will do is we'll match everything after the comma and space, but only extract the name of our state. Let's take a look at what this looks like when we run it. So X looks like California, Nevada, New, and California. And I guess to be a little more explicit, let's take a look at what cities looks like in this notebook. Okay, cities in this notebook has this extra row for Berkeley, California, but it doesn't really matter for the purposes of this question. So what's the issue with the regular expression we have and the regular expression that's in the solution? This is what's in the solution. It's matching everything. It's only matching letters, right? And so when it sees the space in New Jersey, it stops matching. And so it only takes the new in New Jersey. So I guess a workaround to this, there are several, and I guess some are more specific than others. You could just change this to be a dot. Okay, and so when I do that and I look at X, it gives me New Jersey, but it just gives me everything after the comma and space in the string. So if it was like New Jersey space a bunch of garbage, this would also match the bunch of garbage as well. But for our purposes, this looks okay. That's just one thing to be wary of. The solution isn't exactly right. And so now what I want to do, let's not assign it to t just yet. Let's just take a look at what it looks like. As I mentioned earlier, what I want to do is set the index of the names data frame to be full. So because the elements of x correspond with the elements in full. And so that when I do .lock x, the index has to be these things in full. So when I can do names.set index full. And now, when I index into it, the indices will be these full names, and there's only one column, or this is a data frame with one column, and that will be ABBREV. And so let's take a look at what this list looks like. This just gives me California, Nevada, New Jersey, and California's abbreviations. Okay, and this makes sense because, in this order specifically, because we have CA, NV, NJ, CA. So this is working as expected. So if I assign this to T, as we're instructed in the template, and now look at what T looks like. Looks like we're good, right? All we wanted to do was join another column to the city's data frame with the abbreviation of each state name. And it looks like that's exactly what we did. So it seems like we're good to go for the pandas part. So this is the solution. And periodically I'll pull this up as well, just so you know what it looks like. But we'll do everything in the notebook, at least just for number one. And so now we're good there. Now we need to do this exact same thing in SQL. Okay, so we're given that we want to create table T as select blank, blank, and blank. And we know we want 3 columns to be in our table. And so those 3 columns actually correspond directly to city, population, and abbreviation. But a city pop, I should say, and ABBREV, where the ABBREV column, abbrev, is coming from the names table. Okay, and you can see that we're joining names on, and somewhere we're going to have to use, the full name to do the joining. But anyways, I want city, I want pop, and I want the abbreviation as AB, just so that the last column is renamed. From cities, the first 2 are coming directly from cities. The third is going to come from joining on names. And so now the question is, how exactly do I do this join? Okay. And so the first argument in this like thing will be city. Okay, and this is, you can think of this as being my left on. So I want my city to look like something. And the like functionality of SQL behaves kind of like regex. What you can do is provide some sort of pattern that you want to match. Okay, and it's not the exact same syntax as regex, but some of the concepts are the same. So, in regular expressions, the syntax we use to as our catch-all, which means match anything as long as it's on this line, is usually dot star. The equivalent of that is %sign in the SQL like functionality. Okay, so essentially what I'm saying is I want my city to look something like, doesn't matter what comes before, but I want a comma, a space, and then the name of a full state. Okay, so I want my city to look like a bunch of random stuff, doesn't really matter what the name is, a comma, a space, and then something that's coming from the full column. And to be explicit, I mean the full column of the names data frame. In this case, it's a table, I guess. So it should look like something like %sign, comma, space, and then plus something from the full column. Okay, how exactly do I do this plus something from the full column? Well, since there's no full column in cities, I can just say full. Now the question is, how do you do string concatenation in SQL? And it's not by using a plus, it's actually by doing double vertical bars. Okay, just like, in some languages you see or being used like this. In SQL, the way you concatenate strings is by doing the double vertical bar. So what this is saying is, join cities and names for rows where the city value looks something like bunch of random stuff, comma, space, something from full. And so this is how it knows to join Nevada City, California with this row. It'll know to join Carson City, Nevada with this row, so on and so forth. Okay, so let's take a look at what this will look like. And seems like we're good to go. The output looks exactly the same as when we did this with pandas. So we're good. Moving on to part B, what we want to do is create a 2-table column U of cities and their populations that are in states with a population above 5 million. Okay, so what I want is something that looks like city and pop, so like just like the states table, the cities table, but for example, we don't want to include the row for Nevada because we're told that Nevada only has 3 million people, and we only want rows for cities that are in states with more than 5 million people. So you can already kind of guess that I'm going to have to merge this T table with states somehow, because states is the only table that contains population information for an entire state here. Okay, and so that's sort of given to us in the outline. So I'm going to merge T with the states table. And now the question is, what are my left on and right on? And remember, left on and right on are just the columns from the left and right table that we want to look for matches on. And here our left table is T, and I want to use the AB column from T. Right, this is the data frame we created in part A. And my right on is the state column from states, because that's the column in states that contains the abbreviations. So that should be state. And so now the question is, how exactly are we going to do this filtering? Well, first, just to illustrate to you what's going on, let's take a look at what M looks like. So now, in addition to the population of the city and the abbreviation for the state, and obviously these two columns are the same, I have the number of people living in the state in which that city is in. And so, for example, what I can do now is just filter out only the rows where the people value is greater than 5, and that would get rid of my Nevada. So let's do that exactly. So I can say M, where M square brackets people is greater than 5, and this is the typical Boolean array sort of filtering that we're accustomed to in pandas. So now I'm only taking the rows where the people value is greater than 5. And then for the last square bracket, we look at the question again, and it says we want a 2-column table, okay, of cities and their populations labeled city and pop. So we only want to extract just the relevant columns here, which in this case are city and pop. If I run this, we get exactly what we want. We have the cities and their populations, but only cities that are in states with more than 5 million people. Okay, so that's how we do this in pandas. Now the question is, how do we do this in SQL? So we're already given the outline, create table U as select city and pop from T, where AB is in blank. Okay, and so essentially, remember AB is this column of abbreviations. What we want to put in this blank is a column or a list of state abbreviations for the states that have more than 5 million people. So what this inner query needs to return is a column with the abbreviations only for states that have more than 5 million people. And so just that specific task is relatively straightforward to accomplish. So what I want to do is select the state name from states. Right, so I want to select the state name from states where people is greater than 5. Okay, because that'll just give me the labels for the states that have more than 5 million people, where people is greater than 5. And so now this will be, I guess in our example, just CA and NJ. And so now when I run this, I get exactly what we need. This subquery just gives me the abbreviations for states with more than 5 million people. And then I'm saying, okay, select cities and populations where the abbreviation is in this selected list of abbreviations. So that's number 2. And lastly, part 3, we want to create a table with 1 row per state that contains the state's abbreviation and the fraction of cities from the cities table, which is up here, in that state that have a population above 50,000 people. Okay, and you can sort of tell from the template that we're given in the question that we need to group by something, and we can presume that we're going to group by the abbreviation. And this custom aggregate function is going to calculate the proportion that we're looking for. Okay, because we want the proportion of cities in that state that have a population above 50,000 people. Okay, so let's start. So I know that I want population and abbreviation, right? Those are my relevant rows. So I can go in here and just take my population and my abbreviation, and I want to group by abbreviation here. Okay? And so just to be clear, let's take a look at what would happen if I group by abbreviation and then just look at the mean. Here, what it's doing is giving me the mean population for each of these cities, each of the cities in these states, right? So for example, California, it's giving me the mean of 3 and 170. For New Jersey, there's only one city, so it's just giving me that value. And Nevada, I believe we only have one city, so it's giving me its population. So instead of giving me populations, the mean population of all the cities in that state, what I want to do is make this aggregate function give me the proportion of cities in the state with over 50,000 people. Okay, and so how exactly are we going to compute this proportion? Well, my aggregate function is going to take in a series of populations. Okay, so for example, for California, it's going to take in 3 and 170. What it should somehow return to me is 50% or 0.5. Okay, and so my denominator is just the number of cities in California, or the number of cities in that state, which is just the length of S, right? Because S will contain all of these populations. And the numerator should be the number of cities in that state with more than 50,000 people. And so here we will again use the idea of Boolean arrays. And so as an example, this is not exactly what we need to do, but for example, the pop column of T has these values 3, 55, 285, and 170. If I say pop is greater than 100, it will give me a new series of the values false, false, true, true, because 3 is not greater than 100, neither is 55, but both 285 and 170 are. So if I run this, I'll get a new series called false, false, true, true. False, false, true, true. Great. And now if I sum these, when I sum a Boolean array, it treats all of the false values as 0 and all of the true values as 1. So when I run this, I should get 2, which makes sense. So now, in our custom aggregate function, we want to do exactly the same thing, but instead of comparing things to 100, we just want to see if they're greater than 50. So now what this will do is take in all the population values for a given city, or for a given state, and compare each of them to 50. If it's greater than 50, it'll contribute 1 to our sum. If it's less than 50, it'll contribute 0 to our sum. And then this will evaluate to the proportion we're looking for. And so now let's run this, see what we get. And that looks about right. Okay. So it seems like, yep, Nevada only has one city and it has a population of 55,000 people. So it should be, its proportion is 1. New Jersey has one city and its population is above 50,000. So its proportion should be 1. And California has 2 cities. One of them has a population below 50,000. One has a population above 50,000. So its proportion should be a half. And that's exactly what's reflected here. So it seems like we did our job correctly here. Now, lastly, doing this in SQL is a little trickier, but you can see the sort of framework that's laid out for us. We see that we're dividing sum by count star. Okay, and what count star should be is the number of cities in that state. Okay, and so remember, we're selecting all of these things from T, just as a reminder what T looks like. The only thing it really makes sense to group by here is the state, which in this case is AB. Okay, and so the denominator now becomes the number of cities in that state. And so this numerator should evaluate to the number of cities in that state that have a population above 50,000. And so we're going to do casework here, and we're essentially just going to recreate this Boolean array. We're going to compare each value that we're passed in to 50. If it's greater than 50, we'll replace it with the 1. Less than 50, replace it with the 0. And then when we sum those up, we'll get the number we're looking for. And so it doesn't really matter what our case is. We could either make it whether population is less than 50 or greater than 50. Just to keep it consistent with the solutions, I'll say when population is less than 50, then we should have a 0 because it's clearly not greater than 50, so it's false. And otherwise, we should have a 1. Okay, so for each state, what this will do is add up a 1 for each time the city, a city in that state has a population above 50,000. Okay, and I group by the state name, and so this should work, and lo and behold, it does. The values are the same, And the only issue is that the name of the column doesn't really match up, but we're not really told in the prompt that we need to have specific names. So that's how you do this one in SQL. And I believe that wraps up problem 1. And I guess I can just display this here if you want to pause and perhaps copy down the solution or something. But yeah, that's question 1. Great. Now let's move on to problem 2, which deals with sampling and probability. Fair warning, if you're watching this in fall 2019, I don't believe we explicitly covered the idea of cluster sampling, but I still don't think the problem's too out of grasp. Okay? So we're given that we have this population. Everyone has a name and is assigned a cluster, either blue or gold. In part A, we're told that from the population above, suppose we draw a simple random sample of 2 individuals. What's the probability that Ace and Adele both appear in sample A? Okay, so in this part, we don't really care about the cluster. We're just looking at the 6 people themselves. What's the probability that these 2 people both appear in the sample? So there's 2 ways to approach this. One, we can think about each draw of our population. And another way we can think about this is, using choosing, and we'll look at both solutions right now. The first way we can think about this is thinking about the order in which we select these individuals. The event where we happen to sample both Ace and Adele occurs if we first pick Ace and then pick Adele, or if we first pick Adele and then pick Ace. So we could say Ace first, Adele second, or vice versa. We could have Adele first, Ace second. And so the probability that we select Ace first and then Adele second, so first we select Ace with probability 1/6, right? Because everyone is equally likely to be chosen. And then the probability that we select Adele second is 1/5, right? Because we used to have 6 options of who we can select, but since we've already selected Ace, the number of options we have to select from is 1 less. So now the probability that we select Ace second is 1/5. Okay? In the other case, where Adele is first and then Ace is second, it's the exact same probability. Okay? The probability that we select Adele first is 1/6. The probability that we select Ace second is 1/5. Okay, so both of these cases have probability 1/6 times 1/5, and it's the first case or the second case, so that means we add the 2, and so our result is 2 times 1/6 times 1/5, which is the 6th option on the sheet. Okay, so that's one approach to solving this. The other, again, as I mentioned, is by choosing, right? We have 6 people, and we want to select 2 of them. So the total number of ways we can do that is 6 choose 2. Okay? And the event where we select both Ace and Adele, you can think of that as being 2 choose 2, right? We're limiting our scope of people that we can choose from as being just Ace and Adele. The number of ways we can choose both of them is just 2 choose 2, which is 1. Okay, and this ends up simplifying to 1/15. Which is exactly what 2 times 1/6 times 1/5 is, right? Because in 2 times 1/6 times 1/5, the 2 and 1/6 become a third, and you get 1/15. So both approaches lead to the same answer of 2 times 1/6 times 1/5. In part B, we're told that we separately draw a cluster sample B from the same population based on the cluster column. What's the probability that Ace and Adele both appear in sample B? So now here's where we need to know how cluster sampling works. The way cluster sampling works is that we, separate our population up into groups called clusters, and then we use simple random sampling to select one or more of these clusters. Okay, and then once we have our selected clusters, we sample everyone within those clusters that we selected. Okay, so here we have 2 clusters, blue and gold, and what we're going to do is just pick one of those clusters and then sample everyone in the cluster. So if we happen to choose gold, we will sample Bella and Buzz. If we happen to pick blue, we will sample the 4 people whose names start with an A. Okay, and so Ace and Adele, like the event where we select Ace and Adele is the same as the event where we select the cluster blue, because if we select the cluster gold, they're clearly not going to be in our sample. Okay, so this just reduces to the probability that we select the blue cluster, right? Since we have 2 clusters total, and since we're doing simple random sampling, so everyone has an equal probability of being chosen, it's equally likely that we select blue or gold. Okay, so the probability that we select blue as our cluster is 1/2, and so thus, the probability that Ace and Adele both appear in our sample is 1/2, right? Because the event where they appear in our sample is the same as the event where our cluster is blue. Cool. And so in part C, we're told that we combine all individuals from sample A and sample B into sample C. What's the probability that Bella appears exactly once in sample C? So one way to think about this is, first we, do the sampling technique from part A, where we just select 2 individuals at random using simple random sampling and write their names down. Then we put them back, and then we do the procedure from part B, which is where we select a cluster. Okay, we either select blue or gold and then sample all of those people. Okay? The important thing to note is that it's possible for there to be overlap between who we choose in sample A and who we choose in sample B. Okay? So we write down the names of whoever we choose in sample A, put them back in, then run sample B, and we look at all of the names that we've written down. We want the probability that we only wrote down Bella's name exactly once. I shouldn't say only. We want the probability that we wrote down Bella's name exactly once. And so, for her name to be written down exactly once, we either had to sample her in sample A and not B, or not A and B. Okay? So to be a little more explicit, we can go over here and say the probability exactly once is the probability that we sample in A and not B, or not A and B. Okay, and since the sampling techniques in A and B are completely independent, since we're putting the people back in after sample A, I can split apart these ands into products. So I can say it's the probability we select her in sample A times the probability we don't select her in sample B, plus the probability we don't select her in sample A times the probability we select her in sample B. Okay, and notice I only really need to find the probability we select her in A and the probability we select her in B, because then not A and not B will just be 1 minus those quantities, which is nice. Okay, so the first question is, what's the probability we select Bella in sample A? Well, again, there's 2 ways we can think about this. Either by looking at the sequences of steps that we need to make to create our sample, or by thinking of this in terms of choosing. So the probability, and to be clear, we're looking at part A. The probability that we select Bella is the probability that she's the first person we select, or the probability that she's the second person we select. Okay, so the probability that we select her is the probability that she's first, plus the probability that she's not the first, times the probability that she's the second. Okay? Given that she's not the first. Okay? The probability that she's the first person we select is 1 out of 6, right? Because all 6 of our people have the same probability of being chosen, right? Because we're doing simple random sampling. So that's 1 over 6. Plus, now the probability that she's not the first person we select is then just 1 minus 1 over 6, right? So 5 out of 6. And another way of thinking about that is, if she's not the first person we selected, one of the other 5 people had to be, so that's 5 out of 6, times the probability that she's the second person we selected. Well, we had 6 people to start off with. One of them was already chosen to be the first person, and so now the total number of people we have to make up our denominator is 5, and she would be one of those 5. So the probability that she's the second person we select is 1/5. And so now the 5 on the numerator and denominator cancel, and this actually gives us 2/6, or 1/3. Okay, so that's how to think about it in terms of a sequence of decisions. Another way we can think about this is in terms of choosing. Again, just as we mentioned when talking about part A, the denominator is 6 choose 2, right? Because we have 6 people, we want to pick 2 of them. Our numerator is actually a product of 2 things. First, we're fixing that Bella is one of the people that we're selecting. So that's one choose one. One person, we're selecting them. For the other person we select, right, because we're selecting two people, there's 5 options of who they could be, and we want to pick one of them. Okay? So the numerator is really just 5 choose 1, because we're fixing that Bella is one of the people that we're selecting. 5 choose 1 happens to be 5. 6 choose 2 happens to be 15. And this also reduces to a third, which is nice. So the probability that Bella is chosen in sample A is 1/3. Okay? So this over here is a third, and this over here is 2/3. Great. Now we want to look at the probability she's chosen in sample B. This is just a half, right? Because for her to be chosen in sample B, we just have to select gold as our cluster as opposed to blue. We saw when doing part B that both clusters are equally likely to be selected, and so the probability that she's selected in sample B is just 1/2. So both of these probabilities are just 1/2. And so when we work this out, we get a third times a half, which is 1/6, plus 2/3 times a half, which is 2/6. That adds up to 3/6, which is a half. So the probability that she appears exactly once in this sample, so the probability that we write her name down only and exactly once, is 1/2. Oops. And that wraps up number 2. Problem 3 deals with regular expressions or regex, so I thought why not go on to regex 101 and play around with the options that we have. Okay, so I've inputted here the regular expression that you were given on the exam, but all of the underscores are replaced with spaces, and I believe that during the exam we gave a clarification where we said that the underscores really mean spaces, but since both space and underscore are literals, it actually wouldn't matter which interpretation we use. But we'll stick to spaces. Okay, so the regular expression we have square brackets a dash z plus. What the square brackets a dash z means is that that'll match any lowercase letter. And since I have that in square brackets and a plus, remember the plus means match one or more of the thing that came immediately before. So what this first thing is matching is one or more lowercase letters. The space, as I mentioned, is a literal, so it'll match that exactly. We follow that up by, again, a square brackets around A to Z with the curly bracket 2. What the curly bracket 2 means is match the thing that came before it exactly 2 times. Not up to 2, not more than 2, exactly 2 times. So we want exactly 2 letters, and then again in square brackets we have space and R. And so the typical usage for the square brackets is it'll match something, some character that's in the square brackets. And here in the square brackets, we have a space and an R. So what this will look for after my 2 characters after the first space is for another space or an R. So one thing we'll need to look out for in these options is after the first sequence of lowercase letters and a space, in that second block, the third thing should either be an R or a space. And if it's not going to be a valid match. So after the R or space, I have space question mark. And so what the question mark meta character does is that it matches 0 or 1 of the thing right before it. Okay, and so this case, that means 0 or 1 spaces. So notice this will actually match a string where I have, some number of lowercase letters followed by a space, by 2 more lowercase letters, followed by 2 spaces, right? Because I could take the space from here and the space from here. Okay, but you don't need the double space in order for it to match. I'm just saying that it would match. We followed that up by, again, square brackets A through Z, plus, which means 1 or more lowercase letters. So, I know I have the solutions up here so you can see which ones are right, but let's go through each of the options and talk about why they're right or why they're not right. So bar chart. This one doesn't match, okay? And so up until this point, we're good, right? Because we have some number of lowercase letters followed by a space. So what really we need to look at is the second sequence of chart. Okay, so now we're really looking here. Okay, I have 2 lowercase letters, so C and H, which is great. But now the thing after the two lowercase letters C and H needs to either be a space or an R. Here, it's an A. Okay, so since after my two lowercase letters, I don't have a space or an R, it's not going to match this. So that's why bar chart doesn't work, isn't matched by this regular expression. So bar chart is not correct. Group by X does work. Okay, and let's walk through that. So group space works, right? Because, that's any sequence of lowercase letters followed by a space. Then I have my two lowercase letters, my B and Y, and the thing immediately after that is a space, which is allowed, right? Because the thing right after it has to be a space or an R. In this case, it's a space. In this case, there happens to not be a second space, right? So the question mark is matching the fact that there's only one space here, not two. Well, so really it's 0 in this case, right? Because we have 0 or 1. I'm taking the space from the first choice, I guess, so I'm not taking the second space. And then I follow that up by one or more lowercase letters. So this works. And so to elaborate a little bit more on the whole notion that I could have two spaces, if I add a space here, it actually still matches. Because now it's taking the space from this set of space or R, and then it's matching 0 or 1 spaces after that. If I add another space, it's not going to match because now I have 3 spaces, but this only will match up to 2. Okay? But the option only had a single space, group space by space X, and this works with that. So group by X is a correct option. Now let's look at a box plot. This also doesn't work for a similar reason as bar chart, and it really has to do with the second block of letters. The third thing in the second block is neither a space nor an R, so it's not going to work. And visualize first. This works because in the second block, the third thing is either a space or an R. In this case, it's an R. And then after it, we happen to have 0 spaces, which is fine, because this will match 0 or 1, followed by 1 or more alphanumeric characters. So this would actually work if I put a space after the R, because in that case, this would get matched, right? Because here we have 1 space as opposed to 0. So this actually works. I could also get rid of the R and just have 2 spaces, and that would also work. And it doesn't really matter what comes after here, as long as it's all lowercase letters. But the option we were given, FIRST, works perfectly fine because the third thing is a space or an R, followed that up by 0 spaces, in this case 0, but it would match 0 or 1, followed by at least one alpha, or at least one lowercase letter. So visualize first also works. So the correct options here were group by X and visualize first. Great. Now let's move on to the data visualization question on the exam. Okay, so in 4A, we're given 2 histograms, and we want to determine whether or not these 2 histograms are displaying exactly the same data. Okay, and so admittedly, this type of question ends up being very tricky, and if I were thinking about this as a student, my natural inclination would be to assume that it's impossible to tell unless there's concrete proof that it's yes or no. Okay, and so in this case, the answer actually ends up being no. We know for sure that they're not displaying exactly the same data. And here's why. We notice, upon observation, that both of these histograms have exactly the same bin size, or like the width of the bins is exactly the same. Okay? How do I know this? Well, it's because a change of 5 in the x-axis in both graphs correspond to 2.5 bins, right? What I've underlined in both the left and right histogram is 2.5 bins. And they both correspond to a change of 5 in the x-axis. So we can see that both histograms have the exact same bin widths, okay? And their bins happen to be centered on exactly the same things as well, right? So we have a bin that's immediately to the left of 10. So let's compare those 2 bins. So to be clear, I'm comparing this bin and this bin. The bin immediately to the left of 10. Okay? In the left histogram, we see that the height of this bin is somewhere over here. Okay? Somewhere between 0 and 10. Whereas the height of the corresponding bin on the right histogram is somewhere between 20 and 30. Okay? If these were the same data, since the bins are the exact same, the heights of these bins would also have to be the exact same. Okay? But since they're not, we know for sure that this is not the same data. If the width of our bins were different, then all bets are off and we couldn't really tell. But since the width of the bins are the same and they're centered at the same places, we can make these assumptions. So since the height of the two bars that I've colored in are not the exact same, I know for sure that these are not displaying the same data. B gets a little trickier. Are the two Gaussian kernel density plots below displaying exactly the same data? Circle only one answer. In this case, it's actually impossible to tell. And so let's reason about why the answer could be yes and why it could be no. The two kernel density estimates look quite different. Okay, so I don't think it's too much of a stretch to say that they could be displaying different data. Okay, so we won't argue too much about that. The question is it possible that they are displaying the same data? And the answer to that is yes. The reason they look so different, or the reason they might be looking so different, is because they have dramatically different bandwidth sizes. Okay? And remember, bandwidth, or alpha, sort of tells you how wide the kernels that we're placing on each of our individual observations is. The larger that alpha is, the more smooth our resulting kernel density estimate will be, but also the less specific it will be. Okay? So it's very possible that these two kernel density estimates are coming from the same set of observations, but since the alpha on the right is much smaller, it's a lot more granular, and so it ends up looking this different. Okay? One question that I believe students asked about on Piazza is, well, how can they be different, how can they be displaying the same information if the height corresponding to x is equal to 0 on the left is around 0.4, right? Whereas the height corresponding to x is equal to 0 on the right KDE is around 0.8. The heights are different, so how could they be displaying the same data? And it's because you can think of the kernels that we're placing on each of our observations as a rectangle with a fixed area. Okay? Smaller alphas correspond to narrower but taller rectangles. Right? If you think about a rectangle, if I pull it apart with a fixed area, it's going to become shorter. And if I compress it, if I squeeze it, it's going to become taller. Okay? The reason it's okay to think about kernels in this form is because we have the restriction on our kernels that they always have to have an area that integrates to 1. Their area under the curve has to be 1. Okay? And so, if something has a fixed area and you make it narrower, it's going to become taller and vice versa. And so, it's very plausible that these could be displaying the same data because the height above x is equal to 0 is much taller on the right histogram, the right kernel density estimate, than it is on the left. And that makes sense because the alpha is smaller, so it would be narrower but taller. Okay, but again, we don't know for sure. And so that's why the answer is impossible to tell. We just reasoned about why they could be displaying the same data and why they could not be. Cool. Part C, which of the following can be determined from looking at this pie chart? Circle only one answer. And again, this is another intentionally tricky problem. Okay? What sort of gives it away is that we tell you can only circle one answer, but options A and B mean the exact same thing. Option A says that B is twice as frequent as A, and option B says that A is half as frequent as B. But these two things mean the exact same thing. But since you can only select one answer, both of these have to be wrong because it would be weird to only select one of these, since they mean the exact same thing. But that was more of a meta approach to tackling multiple choice exam problems. The more direct reason why neither of those are the right answer and why C is the right answer is because in pie charts, it's very, very difficult to compare frequencies. And the reason for that, and I believe this was mentioned in lecture, is that we as humans, we're really good at looking at differences in length. Okay, so if I have, two lines, I can tell one line is twice as long as the other, and we can do that pretty precisely. But it's really hard for us to compare areas. Okay, so it might look like this sliver for A, this sliver for A is exactly half the area of the sliver for B, but there's no way of knowing for sure. It could be the case that the sliver for A is 60% of the sliver for B. And since we're not great at looking at areas, it's sort of hard to know this exactly. Okay, so the main point of this question is, realizing that it's very difficult to precisely read anything off of a pie chart, all we know for sure is that the sliver for B is bigger than the sliver for A, and that seems pretty obvious. And so option C is the correct answer, because there's only one correct answer in this question. Okay, so that one's also a little tricky, but hopefully it makes a little sense now. Option D, you have 30, and the fact that we only have 30 will be important. Unique observations of a real valued quantitative variable. So we're told that we basically just have 30 numbers. Which of the following visualizations effectively depicts the distribution of these values while retaining as much information as possible about the original data? Okay, so it's going to be really important that we only have 30 observations and we want to retain as much information as possible. So first, we can get rid of the pie chart as an option, okay, because a pie chart doesn't really apply to the case where we just have several real valued quantitative variables. Okay, or sorry, one real valued quantitative variable with several points, I should say. A pie chart is more for when we have two variables, one being numeric and one being qualitative, like a label, and with each label we have associated some frequency. That's not what we have here, so a pie chart doesn't really apply. And so now we need to choose between a strip chart and a box plot, both of which apply in the case where we have real valued quantitative variables. The key here is that we want to retain as much information as possible and that we only have 30 unique observations. And for that reason, we're going to go with the strip chart as opposed to a box plot. Okay, so remember, a strip chart kind of just looks like a one-dimensional scatter plot. Something like this. And the height on the y-axis is pretty meaningless. And since we only have 30 observations, it's not that hard to create a strip plot where we can see each individual dot, and that sort of describes to us the entire distribution, and we're not losing any of the any descriptiveness of the data. Whereas if we had a box plot, you know how we typically have markers for the first and third quarter percentile, so like, the 25th percentile, 75th percentile, some measure of central tendency here, and then, a minimum and maximum. That's not describing the entire set of data, right? That might miss, the fact that the data might be bimodal or something like that, okay? That's not retaining as much information as possible. Since we only have 30 unique observations, it's feasible to just create a strip chart and look at all 30 points on our own. And so this difference, between when we'd use a strip chart and when we'd use a box plot is important now when we consider question E. In E, we're given 6 lists, each of a few thousand numbers taking on values in the real line. So now we have 6 separate sets of, thousands of real number data points. Which of the following is the most effective way to visually compare the center and spread of the corresponding 6 distributions? Okay, and the key word here really is effective. We want to be able to, quickly look at this look at this visualization and be able to look at, the general distribution of each of these variables. And so it seems like all of our options are side by side. Right off the bat, we can get rid of side-by-side histograms, okay? Because looking at 6 full-on histograms side by side makes it pretty difficult to compare one histogram to another, right? Because there's 6 of them that we have to look at, and that's perhaps a little too granular because we don't really care specifically about the bins when we're looking at 6 different distributions. We just want a general sense of what the data looks like. So side-by-side histograms isn't really something we would do for more than, 2 different lists. And so now again, it comes down to, do you want side-by-side box plots or side-by-side strip charts? And so in question D, we went with the strip chart because we had relatively few data points, right? We only had 30. And so we were like, okay, seems like 30 is small enough that we could look at all of the points on our own. Now, for each of these 6 lists, we have thousands of numbers. And so having 6, let's just say, vertical strip charts right next to each other. So maybe this could be for list 1, this could be for list 2, so on and so forth. Since in each of these columns we'll have thousands of numbers, it'll be very hard to tell where the points actually line up because there will be the issue of overplotting, right? If you have 1,000 points all laying along one line, and suppose they're all within this relatively small range, it'll be hard to discern differences between different plots because they'll all end up looking very similar, just with a bunch of points on top of one another, right? And so a general idea is this. Like, how are you going to be able to tell the difference between these two distributions when they end up looking similar because we have so many points on top of each other, right? And x is a point here. And so the reason the answer for here is side-by-side box plots is because regardless of the number of data points we have, the box plot is going to look the same for each, right? It'll, give us our median, our mins and maxes, some outliers, interquartile range, so on and so forth. And having these side-by-side box plots, sorry, my plots don't look that nice, but whatever. You get the general idea. Having these side-by-side box plots sort of summarize, like these box plots summarize the relevant information for us without having to show us every single one of these data points. Because we have thousands of them, that wouldn't be that meaningful. These box plots give us all of the relevant information that we need for a summary. And having 6 of these by no means would be too much to look at. Okay? So that's why the answer for E is side-by-side box plots, whereas the answer for D is a strip chart. Okay, and a lot of it has to do with the number of points that we're looking at in each case. Lastly, let's move on to the dimensionality reduction and PCA question that was on this exam. And as a reminder, if you're watching this in fall 2019, PCA is not in scope for our midterm 1, but if you're watching this at any other point in the future, like, I don't know, spring 2020 or something, then it may or may not be. Okay, so that's just one thing to keep in mind. So we're told you perform principal component analysis on some data matrix D using the following Python code from lecture. The main thing that we really care about here is this decomposition into U, S, and VT. And we're told that the resulting value of S is this array of 3, 1, 0, 0, and 0. And in part A, we're told, okay, suppose we want to draw a histogram of the data's distribution along the first principal component of X. Okay, so we're taking our data, projecting it onto the principal component 1. Which of the following arrays would you visualize? So what this is really asking is, which of these 4 arrays give you the values of principal component 1, the values of that projection? Okay, and so in order to answer this, let's talk a little bit about the theory behind how we interpret PCA. Okay, and so remember, the singular value decomposition, which we sort of just treat as a black box in this class, takes our matrix X and decomposes it into this product of 3 matrices, U, sigma, and V transpose. Okay, and a property that we use that is true of both U and V, but we don't really talk about it for U, is the fact that they're orthogonal. And so what that means is V transpose times V gives us back the identity. Okay, so when I multiply both sides of this equation here by V, I get that X times V is the same as U times sigma. So whatever I can do with U times sigma, I can also do with X times V. Great. And so now a little bit about how to interpret U sigma and VT, or XV, sorry. In this matrix V transpose, the rows of it correspond to the coefficients that describe each of our principal components. So V1 transpose, so the first row of V transpose, corresponds to principal component 1. Okay, and this is the vector that we will multiply X by in order to project onto the first principal component. Okay, the second row of V transpose describes the second principal component, and so on and so forth. So what we want to do is multiply our data matrix X by the first row of V transpose. But that happens to be the same thing as the first column of V. Okay? Right? Because if I take the transpose of V transpose, that just gives me back V to begin with. And so now the principal component vectors lie in the columns and not the rows. Okay? And remember, whatever I can do with U times sigma, I can also do with X times V. But basically, what I want to do is multiply X by the first row of V transpose, or alternatively, the first column of V. And so now let's take a look at the answer options we have. The first one, X times the transpose of U, doesn't really have any meaning, right? The two ways that we project our data onto a principal component are by looking at xv or by looking at u sigma. XU doesn't really have any meaning, so we can ignore that. Now what I want to do is look at both of the last two options first. Okay? What we're looking at here, x times v transpose 0, comma, colon. Remember, 0 is our row indexer, and the colon is our column indexer. So what we're saying is multiply x by the first row and all of the columns of v transpose. And as I mentioned before, that's exactly what we want, right? We want to multiply x by the first row of v transpose, and that'll project all of our points onto the first principal component. So that's exactly what we want. The last option, x multiplied by v, now instead of taking the first row and all of the columns, I'm taking all of the rows and the first column. Okay? And now the reason I'm doing this is because I've transposed v transpose back into v, right? This v t dot t is the same as if I just had some v somewhere. Now what this is saying is multiply x by the first column of v. This is equivalent to multiplying x by the first row of v transpose. So options 3 and 4 are actually doing the same thing. So option 4 is also correct. And notice, this tells us that option 2 is also correct. Because we're doing the exact same thing, but instead of having x multiplied by v, which is what I have here, I have u multiplied by sigma. Right? And from that product, I'm taking all the rows and the first column. Excuse me. So that tells us that the second option is also correct. The reason that we use a star in the second option, but an @ sign in the others, is because the star is for matrix vector multiplications. And here, S is a vector or an array as opposed to a matrix. Okay, and the difference between sigma and S is that sigma is just a diagonal matrix with the entries of S on the diagonal and zeros everywhere else. So when we do full matrices as false, it gives us this S as a list as opposed to a diagonal matrix, but the interpretation is the same. So that sort of justifies why options 2, 3, and 4 are all correct. In part B, we're asked what proportion of the total variance of D is accounted for by the first principal component. And so to answer this, we need to look closely at this matrix S. Not this matrix, sorry, the array. The values of S correspond to the standard deviations of each principal component. What I mean by that is that 3 is the standard deviation accounted for by principal component 1. 1 is the standard deviation accounted for by principal component 2. And 0 is the standard deviation accounted for by principal components 3, 4, and 5. So that means the variances accounted for by each principal component are the squares of the elements in S. What that means is that the total variance in our data set is the sum of the squares of the elements in S, which is 3 squared plus 1 squared plus 0 squared, which is 10. The variance accounted for by just the first principal component is then just 3 squared, right? Because variance is the square of standard deviation. So that's 3 squared, which is 9. So the proportion that's accounted for by the first principal component is just 9 over 10. And hopefully that's clear. Lastly, part C, what is the rank of X? Another interpretation of the elements of the S vector, or the S array in this case, is that they are the singular values of the matrix X. Okay? And one way to think about the rank of X is as the number of non-zero singular values of X. So the rank of X is the number of non-zero singular values. and this fact was sort of talked about in lecture. In this case, we have 5 singular values, 3, 1, 0, 0, and 0. The number of non-zero ones are 2. We just have 3 and 1. So that means the rank of x is 2. And I believe that wraps up the last question on the exam, which means we're done talking about the exam. If you're watching this to study for some exam, which I don't know why else you'd be watching this, maybe for fun, I don't know. Good luck, and feel free to email or post on Piazza if you have any questions. Thanks.